welcome. This is our second Red Talks. Here we have Mrs. Golub. She's an environmental engineer, and she'll be talking about global warming and if it's real, and if it is, what we should be doing about it. So please give her a big round of applause.
Hi everyone, thank you. Welcome, and thank you for Red Talks for inviting me here today. So we're going to try to keep this really informal. If you can't hear me, then raise your hand and we'll speak out. If you have questions during the presentation, raise your hand and ask the question. Hopefully we'll have some time in the end as well for some questions and answers, so you can hold your questions until then if you want to, but it's up to you. We'll keep it informal. Okay, so let's just get right into it. So I want to show of hands who believes that global warming is real, and who believes that global warming is not. Oh, not one. Okay, that's interesting. I've asked this question literally hundreds of times. I've asked this question of children, who's like, young as 10. I've asked this question of teenagers. I've asked this question at conferences, at scientific panels. Friends who come over for dinner, and I almost always get the same statistics. Most people believe that it is real, and some people believe that it is not. However, my goal here is twofold. One goal for this presentation is to convince you that whether you believe or don't believe it is not really a relevant question. What I found is that people's beliefs are not really based in fact. And when I ask them, why do you believe what you believe, they can't really answer that question. So that's goal number one, is to show that whether you believe it or don't believe it is not relevant. And the second question is, of course, to present you with some facts. So we can go ahead and go to the next slide. So the next couple of slides we're going to go through really quickly, and they're just informational slides for those of you who may not know anything about the greenhouse, global warming and the greenhouse effect. Okay, so when we talk about global warming, we're really interested in the greenhouse effect. So the Earth's atmosphere has a lot of various gases in it, and some of the gases act as a thermal blanket, meaning that when sun's energy comes in and then it's bounced back as heat, it's reflected back as heat into space, some of that is reflected back to Earth. And this is actually what keeps our planet warm. Without this greenhouse effect, our Earth would be really cold. It would be about -18 Celsius or 0 Fahrenheit. It would basically be a big frozen rock. So the greenhouse effect is a good thing. When we talk about global warming, we're interested in the enhanced greenhouse effect. And what that means is that we as human beings, we like to drive our cars, we like to go on vacation on airplanes, we like our electricity. All of these things are produced by the burning of fossil fuels. And the combustion of fossil fuels is not a complete combustion process. Some elements, some chemicals do not burn up in the process or are transformed into something else. One of those is carbon dioxide, CO2, and it's a pretty major greenhouse gas that most of you have probably heard about. One thing to note from this slide is greenhouse gases they're not geographic in nature, meaning that whatever we, let's say, emit in America has the same effect in Africa or elsewhere in the world. So what's the big deal? Well, I live in Redondo Beach. I really like warm weather. I like to go to the beach in the summer. I wouldn't mind a few extra warmer days. So what's the big deal? Well, maybe not a big deal for me, but these global warming can cause melting of ice glaciers, and this is something that scientists are worried about, and this is probably something that you've heard in the news a lot about. What happens if the glaciers melt? Well, if they melt, we could have some cities that are flooded, some coastal cities, maybe like Redondo Beach, maybe not. However, we could also have a lot of droughts in countries that are landlocked, maybe some countries in Africa. However, one of the big things that we don't normally hear in the media about is destruction of the Gulf Stream. Do you guys know what the Gulf Stream is? It's like a convection current that carries warm water from the Gulf of Mexico, and it carries it up the Atlantic coast of the United States, and then it splits off. One side of it goes off to Canada, and the other goes towards northern Europe. So the question that a lot of scientists try to figure out is what happens if the Greenland ice sheets melt, and all of that water gets incorporated into the Gulf Stream, and that could very well disrupt the Gulf Stream, and what happens then? But what the models predict is that if that happens, Europe would actually get really, really cold. So it's interesting that some places would get really hot, some places could get really cold, other places could get flooded. So it kind of is a big deal. Some species may adapt and some may not. Human beings will very likely adapt. There'll be a lot of cost, there'll be maybe a lot of human lives that are lost in the floods or tornadoes or hurricanes. But as a species, we would survive. However, some species may not, like that holy little polar bear over there, because they're uniquely adapted to their environment, and they could not survive in a different environment. So causes of global warming, we already talked about this a little bit. We've got both man-made and natural causes. Some of the man-made causes are in this slide over here. It's all the combustion of fossil fuels that we do. There's a power plant over there. Some natural causes may be forest fires, volcanic eruptions. All of those can put up a whole bunch of different greenhouse gases in the atmosphere. This is my only funny slide. Sorry, guys. Believe it or not, the raising of cattle adds not an insignificant portion to greenhouse gases because cattle produce methane in their digestive tract, meaning they burp when they fart, and that's not an insignificant percentage. So I think that says, have some more beef veggies. It makes you laugh. That's my only joke. Okay, this is probably the last technical slide. I just wanted to show that greenhouse gases are not all created equal. So we've got carbon dioxide, which we've talked about before, and carbon dioxide has a global warming potential of 1. Methane has a global warming potential of 21. And what that means is that methane can roughly absorb more than 20 times than carbon dioxide can. So it's a much more powerful greenhouse gas, even though there's not really that much of it out there. And then that shows the contribution. Carbon dioxide contributes about roughly 25% of what we think of as global warming. The other compounds not so much. And then water vapor, we don't have a global warming potential for it for various technical reasons, but its contribution is about 60 to 70%. And of course, water vapor is something that occurs naturally in our atmosphere. And you'll see later on how the interaction between the two is what we're really concerned about. The CO2, remember, most of it is man-made, and water vapor is all natural. All right, so we can think of, and this is a major concept in global climate theory, forcings and feedbacks. So the Earth maintains a balance between incoming solar energy that it absorbs and the amount of heat that it radiates back towards space. Variables that cause this energy balance to change affect global temperatures. They're called forcings because they force temperatures up or down. Scientists are not very great at forcings because they force. So forcings can be man-made, like greenhouse gases like we talked about, like CO2. And they can also be natural. Natural greenhouse gases from like volcanic eruptions, for example, or some other natural causes like changes in sun energy output. Feedbacks, and I think that feedbacks is like if you take away anything from here, take away feedbacks. This is something that you don't hear in media, but this is a major concept of like in global climate change theory. And feedbacks are physical processes that change in response to a temperature change and subsequently amplify or diminish the effects of forcings. That's a technical definition, which is really hard to understand. But these slides, I think, do a better job. So we think of feedbacks as cycles. So let's take water vapor feedback, for example. Here we have greenhouse gases that are injected into the atmosphere, let's say CO2 from fossil burning. And what that does is it raises, creates a bigger thermal range, but just a little bit. And so it raises the average global temperature in the atmosphere just a little bit, not a lot, just a little. But what that means is that more water is evaporated from the ocean surfaces. And of course, water, we learned, is a greenhouse gas. That goes into the atmosphere, creates a thicker blanket, increases air temperature. Now, even if these greenhouse gases are no longer emitted or injected into the atmosphere, the cycle is going to continue because it's self-perpetuating, right? Water is a greenhouse gas. It increases the temperature. Increased temperature means more evaporation, and so on and so forth. Another positive feedback cycle is the melting of ice, and it works in a similar way. You've got greenhouse gases that are injected into the atmosphere. Air temperature increases just a little bit, but it's enough to start this process. What happens is that ice melts. Ice is very reflective, so if you have less ice, then less sunlight is reflected back into space, and more energy is absorbed by the Earth, which means that air temperature increases, more ice melts, and so this feedback continues. Not all feedbacks are positive. Some are negative, but some, like clouds, are really confusing to scientists because clouds, they're the most uncertain feedback that we know. And their formation is dynamic, and the formation of clouds really just depends on the temperature of the land or the water below them, and we just don't really know how or when they form. So this gives rise to actually both positive and negative feedbacks, and it's the scientists have a really hard time determining how these feedbacks, play into the overall climate theory. So, what we know and what we don't know. So here are some of the things that we absolutely know for sure and nobody argues about. Historical data. We have pretty good historical data, and we know the atmospheric CO2 has increased. In fact, it's increased since the late 1700s, the Industrial Revolution, with most of the increase happening since 1950s. CO2 emissions are a result of fossil fuel combustion. Nobody argues that, everybody knows that. And in fact, the other one is that average global temperatures have increased. We have data dating back all the way to 1850s when reliable instrument temperature measurements were taken. And most of the warming has occurred since 1970s, but we have over 100 years of pretty good solid data. However, what we really don't know is the future. We don't know whether temperature will rise by 1 degree, by 5 degrees, by 10 degrees. And we don't know, but we really, really try to predict. And we try to predict by using models, not these models. We use computer simulations. That's what we use to predict impacts. Now, climate models are designed to simulate the responses and interactions of the ocean, the atmospheres, and land. However, they do not always predict accurately, and this is where Cindy Crawford comes into play. So, the uncertainty in these climate models can be explained the same way as we look at fashion models. So, just because a pair of jeans would look great on her, the same pair of jeans may look really different on women. And the reason for that is because the underlying assumptions are different. She has a different body type than I do, and I'm a little older. The computer models work the same way. There's assumptions and uncertainties that we think are going to work one way, but then they don't quite work because we don't fully understand the science behind them. For example, we don't understand what choices human beings will make. Will we stop all production of greenhouse gases? Will we stop some? What will we do? Climate interactions and feedbacks, this is something we already talked about. We don't really know, for example, how cloud feedbacks work. So we put all this information into these computer models, and they spit out a result. And I can run my computer model, you can run your computer model, but if our assumptions are somewhat different, we'll end up with different results. And depending on how sensitive the model is to those assumptions, we could end up with vastly different results. So that's why there's a bit of disagreement about what we see out there. So who's right and who's wrong? Well, many scientists agree that man-made global warming is happening, and that's actually what you guys all said. You guys all agree that you believe that global warming is real. Some skeptics argue that global warming predictions are based on incomplete models. Why all the disagreements? Well,